Welcome to this video. My name is Mark Scythian. The date today is January 12, 2025. This video is going to focus on AC RLC parallel electrical circuit design with respect to motor performance and energy transfer. So we're going to focus on designing an AC RLC parallel electrical circuit to power a 50 brake horsepower AC electrical motor. So the fastest and most accurate way is to implement the optimized resonant circuit method of design. So we're simply equating the circuit's frequency to the resonant frequency, and so upon doing so we can solve for perfect squares of the inductance L and the capacitance C. So upon solving for the perfect squares, we calculate our Henry's inductance, the L, and our Faraday's capacitance, C, as congruent or equal to each other, thus a resonant circuit. Next, we calculate the AC electrical true power at the motor. So we can start by first converting the 50 brake horsepower to its mechanical wattage, 37,300 watts mechanical power, then divided into the AC motor's electromotive efficiency of 85%. So we calculate an AC electrical true power input into the motor of 43,882.35 watts. So since we're matching the L, or the inductance in Henry's, and the C, the farads of capacitance, thus a resonant circuit, we have a power factor of 1.0. L made equal to C, and then resonant frequency made equal to circuit frequency. So then we can use the AC true power formula or equation, which is the effective or RMS voltage times the effective or RMS root mean square current, then times the power factor. This product is equal to the AC true power in wattage. Since we know that value, we can make the equation equal to the AC true power and then substitute the RMS total voltage, 110 VAC, and the power factor 1.0 to then solve for the total RMS or effective current of the circuit. So we calculate approximately 399 amps. So next we can solve for the parallel impedance of this given AC RLC parallel circuit. So we can simply divide the RMS effective voltage total into the RMS effective current total and calculate an impedance of 0.275 ohms. So we know our power factor is 1, and now we know our impedance. Therefore, we can calculate the resistor component in the circuit, which in a resonant circuit, the resistance component should also equal the impedance. So now we can convert our Henry's inductance from its base value to its millihenry's value, 2.65 millihenries of inductance. And we do the same with the Faraday's capacitance from its base value to 2.65 millifarads. So when we're working with the apparent power component, that is simply just the RMS effective voltage times the RMS effective current. However, the true power is the same value times the power factor. So in this case, since the power factor is also 1 across the resonant circuit, we have an equal component value of true power and apparent power, except the units for true power is always in watts, that's the relevancy, and then the apparent power potential is in volt amps. 43,890 volt amps, rounded from precision to accuracy. So our AC true power, 43.89 kilowatts, and our apparent power, 43.89 volt amps. So now we can use the longhand impedance check test method to see if the calculation was in fact accurate. So the impedance of an AC RLC parallel electrical circuit is this equation here. So just to be on the safe side, we'll longhand calculate the inductive reactance, the X sub L, and the capacitive reactance, X sub C. These values should be 1 ohms each, but just to verify the calculation, we can find the equation for the inductive reactance, 2 pi times frequency times Henry's inductance, and substitute these known values and make the calculation, and upon doing so we calculate 1 ohm of inductive reactance. So doing the same with the capacitive reactance, its formula we calculate 1 ohm as well. So now we can substitute the inductive reactance and capacitive reactance values into the impedance equation. And so upon finding their difference in the reactive value of total reactance, we then get 0 squared, or 0. So now we can focus on the 1 over R, its quantity squared calculation. So we take our resistance value, its inverse, 0.275, 1 over 0.275 squared, and we calculate 13.22 plus 0, so we get 1 over 13.22, its square root. And 0.275 ohms as well, so we have matching impedance calculations. So we verified the design parameters as proven correct. So now if we find the inverse cosine of the power factor, we calculate the phase angle that the voltage and current sine waves make on their alternations with respect to frequency. So the 0 degree phase angle implies that the current is neither leading nor lagging the voltage. So they are in phase. So again, a resonant AC electrical circuit design is optimized for heating elements and electric motors. Now, when we get to AC to DC RLC circuits, we may not have that freedom to match circuit frequency to the resonance because of the variances in isolation frequencies, but we don't really run into that with heating elements and electric motors. At least the modern electric motors are really optimized with resonant circuits and a power factor of 1.0. So in the modern world of AC motors, this is very much true. So if we get a little graph sketch of the current and voltage sinusoidal waveforms and their respect to their phase shift and phase angle at 0, we can see that the current and voltage neither lead or lag each other. They're in phase. So we'll have a in phase 0-degree phase angle. So just to get an idea, we have our peak values, peak current and voltage at the crest and trough of the sine waves. So that would be the I and E peaks, negative and positive. And then the effective value that is practically used is the root mean square current and voltage. So the root mean square or effective current and voltage is exactly the square root of 2 times the peak value. So we take the square root of 2, 1.41, we multiply that times the effective values, and then we get the peak. But if we take 1 and divide it into the square root of 2, we then get the opposite, the inverse of 0.707 times the peak value to equal the effective. That is also equal to the cosine of 45 degrees, or 0.707. So just to make it practical and simple, we just take the square root of 2, 1.41 times the peak value at the top and bottom, or the crest and trough of the wave, and this will equate to the effective voltage and current values. Alright, so now we move on to documenting the final calculations. And so in this case, we can reprove that the 43.89 kilowatts of AC electrical true power multiplying itself times the AC motor's efficiency of 85%, then divided into 746 watts, so horsepower indeed equals 50 brake horsepower. So these are the stamps that would be on the motor, the 50 bhp, and the power factor of 1.0, and the impedance value of 0.275 ohms. So now assignment 1 on the list of 1 through 5 is now complete. Moving on to assignment number 2, calculate the AC motor's foot-pounds, torque, and RPM. So the first step is to take the diameter of the output drive on the motor, which in this case it's 0.50 inches, or 1/2 inch. We divide this value into 2 to get the radius of the output drive, or its shaft on the motor, 0.25 inches radius. We then divide this into 2, we divided it into 2 to get the radius. We then divide it into 12 to get the feet, and then we divide it into 3.28 feet to a meter. So that allows us to calculate the meter's radius of the output drive, 0.00635 meters. So then if we solve for the mechanical power at the output drive of the motor, again, we calculate 37,300 watts of mechanical power. This is also equal to 37,300 Newton meters per second of mechanical power. So we're able to take the 37,000 newtons, multiply it times the meter's radius, to then solve for the torque value at a constant RPM. So in this case it's 236.86 Newton meters of torque at some RPM. Next, we can calculate the angular velocity of the output drive, so that is the power divided into the torque, measured in radians per second. So if we take the power of 37,300 watts and we divide it into 236.86 Newton meters of torque, we calculate 157.5 radians per second. Then divided into 2 pi radians, or 6.28 radians per revolution. So this then becomes 25.07 revolutions per second, then times 60 seconds to a minute, and this computes to 1504.2 RPM. And then lastly, we just convert the Newton meters of torque to foot pounds. There's 1.36 Newton meters to a foot pound. So this then computes to 174.2 foot-pounds of torque. So we can then round down, converting from precision to accuracy. So the final values are 174 foot-pounds of torque at 1504 RPM. So number one's complete, and then we will populate the final values for number two, and then we place our stamp placard, 50 brake horsepower, power factor 1.0, and impedance 0.275 ohms. Next, we focus on number three, calculate the constant RPM of the 16-pole AC generator. So the AC generator frequency equation is the AC frequency is equal to the number of dipoles. So dipole is a north and a south pole on the alternator's pole assembly across the rotor and stator. So what's effective is the north and south pole or dipole. So if we have 16 poles and we divide this into two, that would be 8 north and south poles, or 16 divided by 2, 8 dipoles. So 16 poles is 8 dipoles. So now we have 60 made equal to 8 RPM divided by 60. So this equates to 60 times 60 is equal to 8 RPM, or 3600 is equal to 8 RPM. Dividing both sides into 8, we calculate an RPM at the constant speed 16 pole AC generator of 450 RPM. Alright, so now number 4, calculate the gasoline consumption in pounds per hour if AC motor operates at 50 brake horsepower for 1 hour. So we need to know the energy density of gasoline, which is 20,000 BTUs per pound. The industry standard for AC generator efficiency is between 80% to 95% generator efficiency. So we'll take the average value of 87.5% AC generator efficiency average industrial standard, and then our AC true power as calculated, 43,890 watts. We can divide that into the AC generator efficiency. And so then the piston engine has an output mechanical power driving the AC generator of 50,160 watts of mechanical power output from the piston engine driving the generator. So then we divide the 50,160 watts of mechanical power output at the piston engine. We divide that into 1056 watts per 1 BTU per second. So the thermal equivalent to the mechanical drive output is 47.5 BTUs per second brake, but we need to solve for the indicated, the actual input power in the form of burning gasoline. So we divide that 47.5 BTUs per second brake value into the 30% brake thermal efficiency of the piston engine, the gasoline piston engine actually. So this is requiring 158.33 BTUs per second in the form of burning gasoline, then divided into the energy density gasoline, 20,000 BTUs per pound. So every second the piston engine is consuming 0.0079 pounds per second of gasoline combustion, and then this is multiplied times 3,600 seconds to an hour. So we calculate 28.44 pounds per hour of gasoline consumption. And just to get an idea what that is in gallons per hour, we can take fuel density of gasoline, which is 6 pounds per US liquid gallon, and simply divide the pounds per hour into 6 pounds per gallon. So that is 4.74 gallons per hour of gasoline consumption. So number 5, calculate the percent overall efficiency of the system. We know our output power at the motor's output drive is 37,300 watts of mechanical power. We have to calculate the input or the indicated power in the form of burning gasoline fuel. So again, we can use the 28.44 pounds per hour value of gasoline consumption, divide it into 3,600 seconds to solve for the pounds per second gasoline consumption. Then we multiply it times 20,000 BTU per pound energy density. That is a right-o typo there. It should be pounds. 20,000 BTU per pound. And we calculate 158 BTUs per second in the form of burning gasoline times 1056 watts per 1 BTU per second. So the input power in the form of burning gasoline is equal to 166,848 watts of thermal power in the form of burning gasoline. So that's our input or indicated power. So our overall percent efficiency is equal to the output power divided into the input or indicated power, then times 100%. So we calculate 22.36% overall efficiency of the system. So now we'll do the final specifications circuit population, and then this functions as an optimized AC RLC parallel resonant circuit. Thank you for watching this video and have a great day.